The Move Maker app, and our app is the one trying to get a Samsung Galaxy phone to understand checkers using its camera function. Our approach: step 1, find all the corners that define the squares of a checkers board. Step 2, determine if those squares contain pieces. And then your phone knows the checkers board. Alright. So, the way our application activity is set up, if you guys remember from our midterm, we had a built-in camera application. We switched that up a little bit. Now you open up the main activity, you hit the big yellow button, brings up a camera view. When you hit the capture button, it starts our main algorithm in a service behind everything and brings up a activity that says your things are being processed, and you can exit out of that activity, go do other things. And then when everything's done with the main algorithm, it will cut out of that waiting screen and bring the playing activity to the forefront of your stuff. Alright, so starting out, this is Happy Happy World. You remember the main algorithm that we used to start finding corners was crawler. Starts out in the middle of the board, that's the exact middle of the picture, and then it goes to the right until it finds a vertical line. Once it finds a vertical line, it moves up and down them vertically, marking points along as they go. Once it gets done with one line, it moves to the next, all the way till it gets to the end of the board, and moves back. And that is the course that our crawler took for this picture. And those are the points that it found. And it was a nice picture that was very kind to us. And it was great.
For the second part, I just brought this up because lots of times it looks really easy. We see somebody else do it, so I just kind of wanted to ask everybody, can you tell which square goes where? All you get is color, that's all I know. I know a little square, can you pick?
Yes.
They line up like that. That's what I'm looking for. Sometimes you have as little as like 0 to 255 is your color. I have a difference of like 4 that I'm hunting for. So first thing I do is the most important thing is to figure out what the piece isn't. Then you have something you can start building things off of. We try to do no like hard coding. Everything's trying to be dynamic, different colors, different. So we try to have functions to kind of do everything. So what I start with is trying to figure out what the piece isn't. I only worry about the green squares. That was hard to say. So I put these down in all the corners and I look for the one with the lowest standard deviation. Means it has the most even color. I figure that's what the thing isn't. That's really important for me. And then, in the way we're running in right now, I always assume the piece is in the center. I always assume the board's beautiful like this. It's decently square, which can be bad because the more unsquared it gets, you start to have huge problems with how much of the square the piece takes up. So this one's pretty square. All the pieces are in the center. There's no shadows. This is about as happy as it gets for us. So next, I put something out before I run that one. So the other thing that's really tough about this is that if you look at like lots of the piece colors, the major issue is that nothing's uniform. That like right in the middle of a black piece, you have like a big white area. So if that's where I look, I won't get the right colors. So I make the thing in the center big, then I take the average of it. I take what I got here and figure out what's the difference. High enough difference means I found a piece. Thank you, buddy.
Okay, so now that we've seen the nice one, this is our nightmare scenario. This is where we have pieces that are completely covering up a corner. We got things off the edge, we got things off the edge over there, we got shadows. We got one right in the dang middle where I usually start looking for things. There are shadows, there are glare, it's a lot of fun. So, my crawler. These are the points it ends up finding for it, running once. And you'll notice we're missing entire lines over here, a couple points over here, a couple points over there. How do we get to this wonderful situation? Oh man, you remember when it moved up and down, all the nice vertical lines, so nice? Alright, so here are some of the problems we would run into. As it was moving up, it would run into this situation where it would run into the piece, and it just had no way to work around it. It was lost, basically. Not only that, once I find points, I use those points to assume that there's a horizontal line there to move sideways along. So I move along those points, but every once in a while, it would completely miss finding the horizontal line, so it'll just keep moving along it looking for a horizontal line, and that's how I end up missing entire vertical lines in my section, which is not helpful for anybody else. Also, as you can see, yeah, the pieces covering up the edge are very unhelpful. So one of the main things we did is just take the entire set of pixels, flip them sideways, and run the same thing again. So since one of my least robust things is finding that vertical line, and that results in missing an entire vertical line, if you run everything again, turn 90 degrees, you're more likely to find some of those pieces. If you remember the other one going this way, I find some of them down here going the other direction. So when you put them all together, you get a better picture, but it's still not perfect. We're still definitely missing some points up in the top left corner, and then I have to leave it to somebody else to make life better.
So at the point that I get it, Daniel found roughly like 70% of the points usually. Lots of times he can actually find 90% of the points. The problem is that, like he mentioned, lots of the time the points that he finds are just in one line, so he misses entire lines. So we can't really estimate too well from those lines. But that's the problem we have. We have to estimate the points that we can't find from an incomplete set of points, and from that we have to have a complete set of points in a full board. So as you can see, when Daniel runs his algorithm vertically, he finds about 4 of the lines out of 7, so he misses 3. And horizontally, he actually does really well. He only misses 1 line. And so then when you overlap those 2 lines, you actually get pretty much the whole board. But you can actually see that in the top right corner, you're still missing 2 or so points. So we decided to use just simple linear regression. Since they're all in a line, we can estimate where they should be based on that equation of the line. And here is the simple linear regression stuff. You guys are probably not too interested. It uses the really basic y equals mx plus b formula. And the reason that we pick simple linear regression is because it's simple.
And everything's supposed to be in a straight line anyway.
Yeah. And here it's not too much to worry about. It's a little bit of how we actually go about finding the lines. We just estimate lines using simple linear regression and then find their intersects from there. Let's see. So then after we do this, we actually usually end up with a very nice inner board. We actually get all the points that are inside. The problem is that we still have to find all the points that are outside. So if you guys have noticed, we haven't done anything to find outside points. So we have to find a edge guy. So you guys can't see too well, but there's actually an aqua crawler. I place an appendage in the middle of white squares, and then I try searching for a black line. And the way that I do that is I keep on crawling until I reach a threshold that exceeds my standard deviation. And then after that, I just look for the minimum value, and I find the global, and I place a point in the middle of there. And after that, I can apply simple linear regression again, and I can get a very nice picture of the board. And we also have a little bit of error checking every now and then. Sometimes you only get about 2 points in one line. And if those 2 points are close together, which they usually are because of the way the crawler works, they can really skew off and make slopes that are not too bad, but they are bad enough that they really mess up the piece finding.
That's when you need to stop using simple linear
Yes.
regression. Robust linear regression.
That's why you have this. So we actually scan the crawler around points that we guessed, and we try saying, is this a state that it should be in? And then we place a point there.
I mean, multiple levels of kind of iffy data. Every now and then you need to go back and fix. Every area is really small, but about 4 of them all of a sudden it starts to become a bit more of an issue. So I actually want to go back one. Can you go back one? Oh, I went forward one. There you go. Okay, so this is what I'm after. I got to find all those pieces on that board, pick their colors right, and pick them in the right places. For how far over, I assume that if a human could tell what piece it was on, what square it belonged to, I should be able to. So you can actually push these guys over halfway off. Corners, I went pretty... It has to be pretty far in that one. If it gets to the center, it ends up looking like a bow tie, and if it's the bow tie class, I can't figure out what it is, so I assume that mine shouldn't be able to figure out what it is. This was a terrible problem for a long time. And then this got really good. My lines started to get really, really exact. and my lines started to get really, really exact. I figured out before I was always like looking in the square. I built all sorts of things to look on the white square. I broke them down into a ton of different pieces. I tried everything and it just kept not working. And then finally we got precise enough data that I found an easy way. I just lay along all the edges of all the squares. Everything should have a really high standard deviation. It should be huge. It should be almost black on this side and white on this side. I also put check squares here, just in case the line did miss, and I'm all the way on the white, I'm all the way on the other. Then I can check off of that to be like, wait, where am I? So now I have this. I lay it across the squares, and some of those pieces that look like they were going to be really hard to find are actually my easiest pieces to find. Every time, this is where the standard deviation along the edge was below 3. It's normally 60. I mean, it was really a night and day. It gave me the ability to do all sorts of things, and that wiggle room allowed me to be really, really precise. Nice. And then afterwards, I kind of mark all of those as not existing anymore, and then run everything else. So I say if it's not on an edge, then it's in the middle, and I can run everything my good old-fashioned way that works really well. Last thing is if you look at this board, there's a little bit of my head shadow here. Things are pretty dark. Contrast is not high enough. So actually, before I run it next time, I turn it into that. I boost all the colors, I go through, but I don't just brighten it just in case it's blown out. I iterate through it and I normally assume that the center of the board has perfect light. And then I change both sides to match that. So then, if this piece equals a 20, then this piece should equal a 20.
Here's some evaluations. This is a histogram of when you run the crawler and the number of points it finds. All the way over on the left is you found 0% of the points. All the way on the right is you found 100% of them. You'll notice when you just run it horizontally or just vertically, the histogram is very spread out. You get lots down there on the lower end. When you start combining things, you end up getting a lot of things that are up in the 95-100% range. All right.
So last time we talked about the AI, like I told you that it can make valid moves, but it wasn't a very good AI. It didn't make any moves based on intelligence. It just said, well, I have to make this move, so I'm going to make it. So this time we had to make a better AI, and we actually wanted to kind of like show off the AI. We wanted to be able to let the user play with the AI. So now the input is the board and user input, and the output would be a board that reflects the choices of the AI or the human. So how do you make a better AI? We went with the game theory approach. We used the min-max algorithm, which you guys have probably heard of. It's very common. It's like the poster child of game theory. And ideally, a min-max algorithm should use the entire game tree. That way it can actually return the optimal choice. And as you can see there, in our tic-tac-toe example, we have a complete tree for that case. Related works, like I said, the min-max algorithm is the poster child of game theory.
This is the last one on AI, by the way.
Right.
We cut it down.
As such, implementations are very common. We actually found a really nice one in GitHub by a person called Brendan Bain, which was actually really nice because it did everything that we had been searching for. And so that we could focus more on computer vision, we actually ended up using his Checkers AI in our app.
So this is our new app, and this is how it looks like now. We have official logo for our app now. So this would be the welcome screen, and this the user first goes ahead with this, with clicking on this button. This button resets the whole app to perform once again from the beginning, and it leads to this camera activity where the user takes a picture of the checkers board, and as soon as the picture is taken, it moves to the player activity. So in the player activity, this whole checkers board is actually 8x8 matrix of buttons, and each piece is a button, but only those buttons could be clicked which have which have the pieces on those. So the user can click on whichever piece belongs to him, and as soon as he clicks on his piece, he gets to the select king activity where he gets the exact same board, but he has to choose which of the pieces are kings. So The kings are represented with a crown on them, and as soon as user clicks on every king, whether his kings or opponent's kings, and hits the show the magic button, it gets to this activity. It gets to the. In the previous activity, if you notice that this move was possible and this is our piece. So if this move was possible from here to here and user selected all the kings and hit the next button, then this move will move to the desired position as soon as he hits it, and this would look like this. And this is our gameplay activity where all the game goes on, and from this point there is no backing up to the app, and from here the user goes on playing the game and continue. So this activity is also, in this activity also all the black pieces and all the pieces, all the opponent's pieces are open to be clicked. So user can only make the opponent's moves, and AI makes the user's moves. So the AI makes a move, and it is displayed here as for the square from which the AI moved your piece. And as soon as you want to make the opponent's piece, you first click on the opponent's piece that you want to move, and click on the number of places where he bounced. For example, like he's jumping 2 pieces, so he first clicks on. You first click on the opponent's piece and click on the squares where he jumped, and then the last click would be on the destination where he stopped. So, for example, the opponent moved from this point to this point. So the user would click first this, and then the destination, and then move ahead. So, if you know, so this piece was here. So the AI first makes the opponent's move. Then AI also makes makes our move. So this piece was previously here, which is now there, and it's also a king.
Demo. You want to get your webcam started so we can show people what it looks like? On there.
Yeah, sure.
Nice. Should I drag that down here?
No, take it over there.
Yeah, you're just gonna carry that over here. And gotta have that so everybody else can see it on the HDMI.
Oh, sorry. Because that's something you're struggling for a while.
Let's see if it actually works.
Didn't you see it was up there, it was all on the slides.
Photoshop.
Yeah.